heavily defended areas of Southeast Asia, remotely piloted vehicles were used successfully for daylight photographic reconnaissance. The Air Force Avionics Laboratory is testing a night photographic system built by Chicago Aerial Industries. This development effort, funded by the Avionics Laboratory, is intended to improve the night reconnaissance capabilities of remotely piloted vehicles. A horizontal field of view of 120 degrees is scanned by a system of rotating prisms to produce a series of 3 photographs. As each photograph is made, a separate pair of strobe lights, each covered with a dark red filter, illuminates the ground below with infrared radiation. The reflected light then passes through the camera optics and enters an image intensifier tube. This device amplifies the near-infrared radiation 10 times. A photographic film pressed against the rear of the tube records the image. The number of photographs made each second is regulated by the altitude and speed of the remotely piloted vehicle. The system was delivered for testing in an RF-4C centerline pod. This permitted controlled testing at altitudes and speeds normally flown by remotely piloted vehicles. Samples taken from several missions reveal that photographs taken at night with infrared illumination were of comparable quality to reconnaissance photographs taken in daylight. After preliminary evaluation, the photographic system will be installed in a remotely piloted vehicle for further operational testing. Wind tunnel testing programs at AFSC's Arnold Engineering Development Center are now more effective through a man-computer partnership. The engineer now has instant access to the computer's memory and control over its operation by means of a remote terminal. One of the recent programs employing the new system involved studies of a scale model B-1 strategic bomber. Until now, wind tunnel measurements were processed by computer, and the results displayed in tabulated form or as graphs. This consumed considerable time and permitted very few changes during the conduct of the test. An important advantage of the new graphics terminal is that results are instantly available in graphic form during the test. This allows the engineer to influence a test in progress. Testing programs are now more flexible, producing more meaningful data in less time and at less cost. Because of the speed of the system, many more key factors can be monitored regularly, or new combinations can be called up as desired. Test data are displayed on the screen within approximately 4 seconds after the desired test condition in the tunnel is attained. Previously, the time required for converting data into graphic form was 8 to 12 hours. The system is also capable of on-the-spot analysis of questionable data to determine whether it's correct or whether it resulted from an instrument malfunction. A questionable plot may be isolated and magnified, then printed if necessary. Since this information is presented on a TV screen and not in printed form, paper consumption for this phase of the cycle can be reduced by 90%. By producing more meaningful data per test hour, the wind tunnel and test cells are used more efficiently. Mechanical means to connect parts of the system and programs for their operation were developed by personnel of ARO Incorporated, the center's operating contractor. Similar techniques are in use by other aerospace industry organizations in their research and development activities. Current electronic intelligence collection systems receive and process microwave radio signals. The equipment involved is large, and this requires large airframes. Aircraft such as the B-1 strategic bomber can expect a high-threat electronic environment. As this environment increases in complexity and sophistication, there must be a like increase in our ability to cope with it. At the same time, the size and weight of equipment must be decreased, and its accuracy and flexibility increased. Advanced concepts in integrated circuit technology make it possible to reduce the size of microwave equipment. AIL, a division of Cutler Hammer Incorporated, is applying these concepts in a study and development program under the sponsorship of the Air Force Avionics Laboratory, Wright-Patterson Air Force Base, Ohio. The goal is to provide high-performance space-limited aircraft with large-scale electronic intelligence collection systems. The key to this miniaturization is to reduce the size of microwave hardware, such as these waveguides and coaxial circuits, through an advanced design and fabrication approach. The advanced concepts involve combining solid-state circuit elements with thin-film conductors on a high dielectric ceramic substrate. The substrate wafer is 25 thousandths of an inch thick. Conductive material, usually copper, is deposited on both sides. Photographic and etching processes establish the conductor geometry of the circuit elements, which form microwave transmission lines. The impedance and transmission characteristics are a function of the geometry and spacing of the conductive elements and their dielectric properties, unlike conventional integrated circuits. After etching, the circuit components are mounted: chip diodes, chip capacitors, resistors, and transistors. With the substrate assembled in its housing, gold ribbon is welded to the components and conductors. These modular component wafers serve as building blocks in highly sophisticated equipment units. The advantages are small size, lightweight, low power consumption, improved resistance to shock and vibration, and high reliability. Computer control radio frequency testing is one of the quality assurances, and it contributes to the low cost of the microwave integrated circuit elements. The final objective of the study and development program is a prototype model of a threat detection and analysis receiver system. A laboratory model was assembled to validate the advanced concepts and to verify its performance. The production model of this receiver could occupy 1/10 of a cubic foot. Microwave integrated circuit technology is a very promising avenue toward the goal of size and weight reduction and a significant increase in accuracy and flexibility. The increased size and speed of modern high-performance aircraft require improved radar housings or radomes. The radome has become a structural part of the aircraft, as well as an integral part of the radar system. Radomes are usually made of molded fiberglass, which lacks the necessary strength and resistance to high heat. Air Force-sponsored programs reveal that materials such as quartz fabric, impregnated with polyimide resin, offer the desired strength and resistance to high heat. In addition, these materials are less vulnerable to damage from dust, rain, hail, and other environmental factors. The Brunswick Corporation, under the sponsorship of the Air Force Materials Laboratory, Wright-Patterson Air Force Base, Ohio, engaged in a program to establish new or improved manufacturing processes for radome fabrication. The process begins with an inner skin of 4 layers of quartz fabric applied to the radome form. Nylon filament is wound over this laminate, and it's cured in the autoclave. Between the inner skin and the outer skin is a core made of polyimide foam. The foam is a blend of polyimide resin, aluminum powder, hollow glass microspheres, and chopped glass fibers for reinforcement. The mix is formed into contour-matching tiles on epoxy glass forms and cured in a 2-step process. The tooling is simple, and the process minimizes distortion. Use of the foam tiles produces a radome nearly 45% lighter than solid wall radomes. After cooling, the tiles are checked against the mold. The tiles are assembled on the inner skin and the seams grouted with foam. The outer skin is applied in the same way as the inner skin, and the final assembly is sprayed with a coating to reduce rain erosion. This process offers the advantages of low cost and simple tooling. These aircraft radomes are strong, lightweight, resistant to high heat, less vulnerable to environmental damage, and most important, they form an electromagnetic window, transparent to radar signal transmission and reception. Air Force flight tests verify that these high-temperature reinforced plastic radomes meet all objectives and requirements. As an outgrowth of this program, Northrop Corporation is purchasing 60 radomes made by this process for operational use on the F-5E and F-5F international fighter aircraft.